Hello, this is Mr. McMurray, and we are welcome to Chapter 6, talking about energy. But first, we're going to talk about work, okay? Work has the force applied over a distance, okay? Now, the force has to be applied over the whole distance, okay? So it's only the time when the force is being applied over a distance. But anyhow, work, according to physics, is force times distance. Okay, I can push against this wall, but if it doesn't go anywhere, even though I'm exerting a force, and even though I'm going to get tired by doing that, it is not going to be work. I technically haven't done any work. Okay, but if I supply a force to go up the stairs, like
What do you
this
need?
head you're going to do, we'll let you demonstrate. You can just go ahead and do our demo. Okay, going up.
I'm ready for my close-up.
All right.
All right, let's back out of it.
That's good. All right. I thought, well, nobody usually stirs, but of course, it seems like about every 2 minutes it comes up. All right. So when she came up the stairs, she was using a force, the force equal to her weight, to come up the certain distance of the stair. Discussing about 10 feet or so here. Okay. So that force times the distance would give you the units of her work. Okay. Now, we can come up the stairs slowly, or we can go up the stairs again very fast, okay? But if you take the amount of force, well, if I weigh 940 newtons, I think we said the other day, that's the amount of force it takes to lift my body up. And if I go up the same number of stairs, the distance is the same. So force times distance, if the force is the same, the distance is the same, the amount of work is exactly the same. It doesn't matter if I come up slowly or if I come up quickly. As far as work concerned, it's exactly the same. Okay? Now, but something will be obviously different. If I have to run up the stairs, I get a lot tired. Okay? And that's because I've used more power. Power is work divided by time. Okay? So work is force times distance divided by time. All right? And so the faster I do it, if the bottom number of the fraction is smaller, then that means it takes bigger amount of power. Okay, so if I say I have more power, that means I can do the same amount of work faster, or I can do the same amount of work in less time. Okay, or I can do more work in the same amount of time. Either way, that would mean that I have more power. All right. All right. So if you had your head twisted trying to watch the last video or turn your computer on its side, you can now straighten it back up to the front ways. All right. So basically work, which is force times distance, force is in newtons, distance is in meters in the metric system. So we would say Newton meters, N times M, Newton meters. I usually say N dot M. Okay. So that would be the units for work. But that's kind of confusing sometimes. So scientists said, hey, let's just come up, work's important, let's just come up with its own unit. Instead of Newton meters, let's call it something else, which is joules. Capital J is a symbol, Joules, not Jewels. That's the kind of jewels you put in the crown or something. Okay, different kind of jewels. All right, this is named after a French scientist, physicist who studied, guess what? Work. That's right. Okay, and so in his honor, they named it that. Now, joules, or Newton meters, divided by time per second, okay, is called watts. Okay, so joules per second, Newton meters per second, whatever you want to call it, is called watts. So we talk about light bulbs, which are kilowatts, okay? And so forth. That's usually where we hear the word watts. But watts is just a measure of power, okay? How powerful something is. Now, when you hear power on say a Chevy commercial, that doesn't really mean a whole lot, okay? They just, oh, it sounds more macho. Oh, we got more power. But technically, it would mean that either they could haul a certain load a certain distance faster than someone else, or they could haul a bigger load the same distance same distance in the same amount of time, and that would also be faster, okay? Or the same load in less time, okay? So those kind of things would actually be what it means. Technically, when you see it on TV, just like a lot of things on TV, it's just advertising. It doesn't really mean much. But in physics, that's what power means, all right? So key things, if you're putting force on something, it has to move. We said push against the wall. Not moving, then you're not doing any work. Not saying you're not putting forth effort. Not saying you're going to get tired. If I had a big heavy weight pushing on me and I'm trying to push it up, even though I'm not going anywhere, I'm definitely getting tired. I'm putting energy into it. I feel like, and I'm doing work. I feel like, but of according to physics, you only do work if it moves, and it has to move in the direction of the force. So, for example, say I have a bowling ball, which I do. I always do. I can go anywhere without my bowling ball. All right. If I'm holding this and I walk forward with it, am I moving a distance? Yes. Am I exerting a force on the bowling ball? Yes. Okay. But it is not moving in the direction of the force. I'm holding it up, but the ball's not moving up. The ball's moving forward because my legs are moving. I could argue my legs are doing work on me and the bowling ball because I'm holding all of that, but my arms are not. Okay. The only way my arms would be doing it would be if the force moves it a distance. And so if I move it up, then yes, now I have a force exerted over a distance and I have work. If I'm just holding it here, technically, there's no work done. Once again, not saying there's no energy involved, not saying I'm not going to get tired, but it is saying there is no work done. All right, now we have two bowling balls. This one's a 16-pounder, this one's only a 12-pounder. Okay, if I lift both of these, I'm doing work on both of them because they're moving in the direction of the force that I put on them, at least until I stop. Okay, and so as I'm going up, I'm putting force on them. Which one's doing more work? Well, this one, because it takes a greater force to lift the 16-pounder than it does the 12-pounder. Since they're going the same distance, like so, okay, then the heavier one, the more force it takes to lift it, and it's going the same distance, so it's going to have more work. Now, I'm doing it in the same length of time. So if I do this more work with this one in the same length of time I do it with this one, then that means I'm going to have a bigger number divided by the seconds, half a second, whatever it was. And so this number is going to have more power. Okay, if I do it in the same amount of time, more work in the same amount of time, then this one is going to have more power. All right, and you would be surprised if you ever ran out of weights, just get some bowling balls. They will get you tired in a hurry. All right, on to the next. All right, we've been talking about energy and work, and the reason is it takes energy to do work. Okay, we say that work is officially the ability to cause change, all right, or the ability to do work, okay? In physics, usually talking about doing work, so we do that. If we talk about chemistry, like well, next semester, should you be here, hopefully you will be. But if you're here for chemistry next semester, we'll talk about causing changes, all the different kind of chemical changes and explosions and bombs and all the good stuff that happens in chemistry, okay? So since energy is used to do work, we measure it in exactly the same units, okay? Newton meters or joules, okay? So if we know how many joules of energy something can produce, we know that it has enough energy to do a certain amount of work. If we know how much joules of work it takes to do it, we know if the motor or whatever is going to have enough energy to do the work that we need it to do. And so they're basically measured in the same units. All right, now, kind of actually going through this, hitting the high points. Don't forget to watch the more in-depth videos on the other side. Basically, talk about energy. There's lots of different kinds of energy. Probably the one we most remember from, about 5th, 6th grade, somewhere in there, potential energy versus kinetic energy, all right? And hopefully everybody remembers that potential energy is energy that is stored, right? Exactly, I knew you had it. All right, and kinetic energy is energy of motion when things are moving. But let's talk about potential energy first, okay? What is potential energy? Basically, it's the idea of storing energy. Okay, now normally we think of that in terms of position. Okay, and to be honest, having to do with gravity. All right, so I get my bowling balls, which rolled off here. Okay, if I have my bowling ball, if it's right here, it has the potential that if I let go of it, gravity is going to pull it down to the ground. I had to lift it up or use energy to get it up here, and now the energy is stored by the fact that it's off the ground and has the potential to fall down now. Okay, if I bring it up, I have increased the potential because now it has even more energy and it hurt my toe even more if I were to drop it up here because it has more, energy. All right, and so that's normally the type of potential energy we talked about in probably high school, but at least certainly in junior high. All right, but technically that's only one kind. That is GPE. Okay, I'm going to write that down right now. You can look that up in the other notes. But GPE, that does not mean general PE or physical education. That's no one likes doing that. That's dodgeball and all that stuff. You remember that? Sitting in the bleachers in the gym half the time, whatever. Depending who you had. If you had a good teacher, not for PE. But GPE, gravitational potential energy. In other words, because of its position above a surface, then it has the potential to fall and therefore release that energy. And so that energy has been stored due to its position. All right, let's do a little quick waltz around here. All right, now, if I stand over a table, which you may not be able to see there, okay, trust me, it's there. Okay, it's stable. Well, when I had it over the floor over here, it has about 4 or 5 feet to go down to the ground. 4 feet, say. All right, not that tall. And if I put it over the hip, now it only has 6 inches. So what has happened? I have reduced its potential because of its position. Now, granted, to be honest, it would probably roll off the edge and then fall down and hit the ground and still have almost as much potential energy as it had before. But it's always based on the surface. How far is it from the surface below it? In fact, the formula is the weight of the object times the height of the object. All right? Or the weight is basically its mass, kilograms, times its height above the ground. I mean, times the force of gravity, which is 10 meters per second squared, or 9.8 if you want to get technical, and then times how high it is. All right. So basically, if I had my 2 bowling balls over here, which I don't, the other one's over there, but you'll just imagine the blue one here, the 16-pounder. All right. Even if they're the same height, this one has less potential energy than the big blue one would. Why? Because it has less mass or less weight, because mass times gravity gives you its weight. Okay, the force pulling down on it. All right, the height, though, if I put this one up higher and put the blue one down lower, then they might have the same amount of potential energy now, because one has more weight and one has more height. We could get them to the point where they would have the same energy and would hurt just as bad if I dropped them on my toe. I would love to demonstrate, but I only have 2 sets of toes, and I really like both of them. I don't want to hobble around like an idiot for a week, so we won't do that. All right. Now that is gravitational potential energy. Obviously, it depends on how high it is and how much mass the object has, or the weight of the object. All right. But that's not the only way that we can store energy. All right. So let's look at some other ways. All right. So if GPE, gravitational potential energy, is 1, we also have elastic gravitational potential energy. Not gravitational. Sorry. EPE, elastic potential energy. Okay, elastic, most people tend to think means that it can stretch, which is true, but really elastic means that it will snap back into its shape. Okay, because this rubber band is elastic because it will snap back into shape. But if I stretch it and stretch it and stretch it, eventually it gets to where it won't snap back and it's not very elastic anymore. Kind of like the waistband of your underwear. After a while, it's not very elastic and it sags and falls off because it doesn't snap back like it should. But anyhow, the idea of elastic energy is pulling it out, stretching it, and you are storing energy in that. That way, when I let go, then it snaps back and is changed into kinetic or moving energy and hurts when it hits me. Or if you shoot it at, your neighbor or person sitting next to you or the teacher or whoever, okay? But you can't because I'm online today. All right. So anyhow, that is elastic energy. So it's basically energy is stored when something is stretched, okay? This is kind of a rubber band, wristband thingy. Okay, if I stretch it, then yes, it has potential energy. Okay. Also, if I use, let's get this a little lower so you can see what I'm looking at here. Ouch. Sorry about that. Okay. We have these little things here that have a little cup like so. All right. And if I turn it upside down and I put it down, then it will pop up. And what happens is when this is pushed like this goes down. When it hits, the elastic energy is released and it comes down like this. It hits the desk and it pops up in the air. Okay. Quick question though. What happens if I stick it on my fingers on a flat surface? Any difference? Boom. Well, I don't know if you can see that, but it went up and hit the ceiling and bounced back down. Okay, much higher. Why? It's the same amount of elastic energy, right? But remember, work is equal to the force times the time. Okay? All right. When I put this on a flat desk, as this goes down, it's not until it hits the desktop that it begins to push off. So the force is only exerted for a small amount of time. But when I put it on my finger, As soon as it starts curling back up, it's already touching the tip of my finger right here on the tip of it. So as soon as it starts moving, all the energy or all the force is applied directly to making it go up. And it can push up, action reaction forces, pushing my finger pushes back up, and it has a greater force on it, and so it does more work, okay, and shoots it up a lot higher. All right, okay, so that's elastic energy. Now, it can also be, besides stretching things and they snap back into place, it can also be like a spring, okay, and springs can be stretched and then snap back into place like the spring on a wooden screen door, okay, it stretches out and then slams it back shut, okay, but it could also be that if you compress it, now it has the energy to spring back, okay? And so you're storing energy because it's compressed, all right? An example of this would be shock absorbers, or sometimes you see things like these in chairs that you can lean back and whatever, okay? They take a lot of energy. This one probably came off a car, don't know for sure. But anyhow, something that took a lot of weight on it. And you could compress it, and then it would release that energy to store it that way. Okay, this is just a little thing. I don't know if you can see that very good. It's hard for me to put this right in front of there. There we go. Okay, but it has a whole bunch of little things on it that squeeze together. Okay, and so once again, it squeezes, and then when you release it, it pops the handles back open. Originally, it came from a pair of clippers like this. This one actually has a spring in the middle. So you close it, but then this pops it back open again. So when you get ready to cut something else, boom, you don't have to pull it back open. It will just spring right back open and be ready to go again. Okay, so once again, you're storing energy in it when it's squeezed or compressed, but then it pushes it back. Don't have one handy, I don't think, but another example of that would be a ballpoint pen. Okay, you push down on the pen, it pokes the point out, but it compresses a little spring in there so that when you press it back down, it releases that energy and pulls the ballpoint pen back up. Okay, not a fancy example, but they're everywhere. Okay, it's elastic energy. Okay, all those are types of elastic energy. All right, good news is there's no formula for that. Now the last one is chemical energy. Okay, we can store energy in chemicals. All right. Let's talk about some of that. This would be CPE. We've already got GPE, EPE, and now we have CPE. All right, now if you're excited about chemical energy, not to worry. I think next semester we'll talk all about chemistry. But just a quick thing here. All chemicals, like you see this liquid in here, looks a little like water or something like that, but it's not. It's lighter fluid, so don't drink it. But it just looks like it's there. But everything is made out of chemicals. There's energy holding them together. And if you can make them let go of that energy, okay, then you would have some kind of energy release, okay? Usually a form of heat, but also can, in other ways, light, sound, things like that. Things go boom, all right? But you see the idea, all right? And so when I light this, then that gas, lighter fluid, is basically being changed into giving off energy, okay? It had energy stored in it, okay? And some compounds have more than others, and that's why we can use them for, say, lighter fluid, okay? On the other hand, other things don't seem to have so much obvious energy in it, okay? If you look at a log, you probably don't look at it and think, oh, wow, that looks like energy. But you do know that we could put that, hang on, all right. There is energy in some of these objects, okay? Like a log, okay? A piece of paper. A piece of paper doesn't seem to be pretty stable. It just sits there most of the time, right? But if we were to apply this lighter to it, give some heat, now all of a sudden we have something different. We have lots of heat, lots of smoke, new chemicals. Why? Because the chemicals that were in the paper are being released, okay? And so the energy that was used to hold those together no longer is necessary, which means that it can be released, okay? And we'll throw it in there and we'll see some flames here, but hopefully it'll go out here pretty quick. All right. If you hear the sirens go off, you'll know that it didn't go out very quick, and the shrink should have done something. But looks like we're pretty good. That's the nice thing about putting in the sink. Okay. So basically, most chemical compounds have energy that are holding them together. And when they let go of that energy for whatever reason, because of heat or another chemical has been added to them or whatever that breaks those chemical bonds that hold them together, then they can release energy. Okay, and basically when we want to store energy, we hook bonds together, okay, and we want to release it, we break them apart. Just like food, plants build fruits and vegetables and whatever by binding chemicals together and building chemicals through photosynthesis. We, when we eat it, break it apart, and as we break those bonds, it releases energy, and that's what we use to make our bodies run, okay? And that's chemical potential energy. It's stored energy, all right? Some is easier to get to and release it than others, but it's there for everybody, all right? CPE. All right, I hate that y'all are missing out on all the great uh, burning paper smell that we have here. It's one of the other advantages. Certain kinds of heat, energy that's been stored, it also releases some neat stuff. All right, now the other one is kinetic energy. We're talking about potential. We said we have CPE, EPE, and GPE, all types of storing energy. Okay, but we also have kinetic energy, things that are moving, okay? If I take this bowling ball and I throw it, it has kinetic energy, all right? And the formula for that, which I'm not going to do a whole lot on right now, is 1/2 times mass times velocity squared divided by 2. Okay, forget the half part. Okay, if you just take the mass, how much mass the object has, times velocity squared, and divide that by 2, that will give you the amount of kinetic energy it has, okay? Now, if you think about that, all right, mass, so obviously the bigger the object is, the greater the kinetic energy. If I threw this bowling ball and the other pinkish one over here that's only 12 pounds, if I threw both of them at the same speed down the bowling alley, this one would have more kinetic energy and would knock more pins around. Why? Because it has more mass, okay? Now, if I threw 2 bowling balls like this one, which I don't have, but just pretend it's here, okay? If I throw them and I throw one of them twice as fast, which one's going to have more kinetic energy? Well, obviously, the one that's going twice as fast because it's got more velocity. So if it has more mass or it has more velocity. But notice the one that's going twice as fast will have a lot more kinetic energy. Why? Because the velocity, which is bigger, is squared. So if it's going 2 times as fast, instead of having 2 times as much kinetic energy, it would have 2 times 2, which is 4 times. If it's going 4 times as fast, it would have 16 times, 4 times 4. Okay, so because the velocity is squared, it has the biggest impact on the kinetic energy. Mass does too. If you have twice as much mass, you have twice as much energy. But because you square the velocity, which makes sense, kinetic energy is moving energy, had the velocity or how fast it's moving, as well as the direction, is going to give you have a lot bigger effect on it. So if you wanted to get the maximum amount of kinetic energy out of an object, the first thing you would do is try to make it go faster, increase the velocity, okay? All right, so that's kinetic energy. Now, mechanical energy is equal to the kinetic energy plus the potential energy, all right? And let me set up something real quick, and we'll be back. So here we are. This is our pendulum. We have a heavy weight right here, and I'm swinging it back and forth. Hopefully you can see all that. Let's see how well my staging was there. Okay, now that is a pendulum. Pendulums swing back and forth, okay, and they're excellent things for studying kinetic and potential energy. All right. If I lift the weight up, okay, and it's up in the air over here, then that means that it has what kind of energy? It's just gained, because I lifted it up, increased its position, GPE, gravitational potential energy, okay? I used kinetic energy, I put kinetic energy into it, I moved it up to here, and now it has more potential. If I keep moving it up higher and higher, it would continue to, I would put kinetic energy into it, and I would gain potential energy, all right? Now, if I were to let go of it, okay, then it will swing back and forth, all right, and it will come almost exactly back to the same spot. In fact, if I do this right, if I put it under my chin here, if I do not move, it should not hit. Okay, but it's pretty hard to stay still there and watch that thing coming at you. All right, why? Because the total energy does not change, okay? It has a certain amount of energy right here, okay? Its kinetic energy is 0, we call potential. Then as it goes down, it begins to gain kinetic and lose potential. And then as it goes back up, it loses kinetic and gains potential. But the total amount of energy is the same. So when it comes back here, it should not hit, okay? Or should go any closer. Now, it's also going to have a little bit of air resistance. All right, its drag is not negligible. There's a little bit. And so that's why I can almost guarantee it won't hit me in the chin if I can just make myself stand perfectly Still, of course. So here's the deal, though. The mechanical energy stays the same throughout the whole thing. Let's just say it's 100% or 100 potential right now. Okay, as it starts to fall, it loses potential. Say it's only 50% potential here, but it's gaining kinetic. So let's say it has 50 units of kinetic energy, say 50 joules. So it's still 50 and plus 50 is 100. The total up here was all potential 100 joules. Now it's 50-50. When it's right down here at the bottom, it can't fall any farther unless the string breaks. So as long as the string doesn't break, its potential is 0, but its kinetic is 100 joules. Okay, as it goes back up, the potential energy is increasing. All right, and somewhere over here it would be 50 again, and the kinetic energy is decreasing, so it would be 50. So 50 and 50 is still 100. Then up over here again, right before it starts to come back down, it would be 100 joules of potential and 0 kinetic. The total, the mechanical energy, stays the same. Now, technically, with air resistance, technically the amount of energy would slightly decrease, but it will swing for a long time before it stops because it does conserve the energy so well. All right, but basically kinetic is when it's moving, potential or gravitational potential is when it's up in the air and has energy stored, but the total stays the same. Okay, the same thing would be true if I threw a ball up in the air. Okay, of course I have one. All right, so we have a golf ball. If I have this golf ball, same thing. When I throw it up, as soon as I let go of it, it's almost all kinetic energy. But as it goes higher and higher, it gains potential, but it loses kinetic. It's just like a pendulum, but upside down. Now at the very top, instead of being all kinetic, like this one was, it's all potential. And then as it starts speeding up back down, it starts losing potential and gaining kinetic. Okay? If you were going to hit something with the pendulum, where would you want it to hit? Say a building. Say you're using this like a wrecking ball, which is basically a pendulum. Okay? And you have this wrecking ball. Where do you want it to hit the building? Up here while it's still going down? Right here at the bottom, or over here when it's starting to go back up again? Well, ideally, it'd be right when it reaches the bottom because that's when it's 100% kinetic energy. Okay, so the kinetic and potential energy changes as the pendulum swings, but the total energy, the mechanical energy, stays the same. Let's talk about some of the different types of energy that you've heard of. Okay, some of the most, we've mentioned a lot of these already, but let's just go through them. Obviously kinetic, which is moving, and we have potential. But we also have electric energy, which we'll talk about later on in chapter, whichever, I forget which chapter right now, but we will get to that. Let me get over here with less light. All right, and all the glare. That'll work, maybe. Okay, there we go. Okay, so basically you have electricity. Okay, you have kinetic, we talked about potential. You have heat energy, we talked about that. Sound energy, okay, which we'll also talk about later, and light energy, which we will talk about. Okay, we already talked about chemical, gravitational, elastic, potential. Those are basically the main types of energy. And also, I'm sorry, nuclear. We should leave that in there too. Okay, nuclear energy. All right, so let's talk about some of those real quick. Electricity. Well, what is electricity? It's the flow of electrons through a wire, okay? So as electrons move through the wire, through a circuit, there has to be a circuit, because otherwise they'd all run out, you'd run out of electricity. It's got to go around and around. And as long as there's electrical pressure or voltage, it will move around. So it's moving electrons. So in a way, you could say that electricity is kinetic energy on the atomic level because you've got electrons, or parts, subatomic particle level, okay, that are moving, okay, and because they're moving, it's really kind of a type of kinetic energy. All right, sound, like my voice right now, as my vocal cords vibrate, they move the air molecules and squeeze them together, spread them apart, squeeze them together, spread apart. And so, if there were no air between me and we were out of space, you would hear me say, which you might think would be an improvement, but obviously you wouldn't learn much that way. So it's probably a good thing that you can actually hear me, because in space there are no air molecules to vibrate. So you have to have something that vibrates to carry those vibrations or move to your eardrums. And when those vibrations get to your eardrum, then it sends those signals to your brain. Your brain says, oh, Mr. McMurray said something extremely smart and witty and I should laugh. Okay, or not. But anyhow, so technically sound is also a type of kinetic energy. Why? Because the atoms in the air are vibrating or moving and getting closer together, farther apart, and that's what sends the vibrations that you hear as sound. Light is a little bit different. Light does involve vibrating electric fields and magnetic fields. Okay, so it's called EM waves. Okay, electromagnetic, electric waves and magnetic fields that are vibrating, and as they vibrate, then they send energy. And so, and light can be considered like a particle, but sometimes it's more like a wave. But at any rate, uh, that's another type of energy. And technically, it's kinetic because there are vibrating electromagnetic fields. And so, technically, it's still involved with motion. So, you could say that all those are types of kinetic. Now, nuclear, on the other hand, is kind of like chemical, okay? Except for chemical is between two atoms holding them together to make a compound. Nuclear is inside the actual atom, what holds all the parts of the atom together, in particular, the nucleus with the protons and the neutrons. Okay, very, very strong forces. Okay, so we're not talking about holding atoms to each other. We're talking about holding each individual atom together. And these are extremely big forces. So technically, nuclear could be considered a type of potential energy. It's stored in that nucleus. If you can tear it apart, which is very difficult to do. In fact, we can only do it for mostly uranium and plutonium and a few of these other extremely large, unstable atoms. Then you could release that energy theoretically. That's the idea of fusion and fission and nuclear power that you hear about. That's kind of what it's promising the ability to do. And so it's really a type of potential or stored energy as well. Okay, now I do want to talk about something else too. Is energy sources. In other words, where do we get energy that we use for things? Okay, it's not quite the same. Usually, we're talking about making electricity out of it, so that's really where it usually comes. But our energy sources are things like gasoline, natural gas, coal, oil, hydroelectric dams. Okay, um, um, we'll talk about thermal, geothermal, which means basically heat from the center of the earth, okay, that comes up and heats up water and makes steam, things like that. We have wind, which you see a lot of these windmill parts going, wind turbine parts going out on the highway, big old long blades and the big round parts that make the cylinder that they're on, the support post and stuff. A lot of wind is getting, and then of course nuclear. These are all power sources. Okay, now a lot of people are anti-nuclear, and we've seen like the tsunami, the waves and flooding in Japan. Uh, at the nuclear power reactor there, Chernobyl in Russia that melted down. Back in the 70s, there was not any real severe consequences, but there was Fremont Island in Pennsylvania. There was an issue there. Okay. Frankly, I see at some point we're going to have to use nuclear because at some point we're going to start running out. So far, we've been able to dig deeper, go farther out in the ocean to get more oil and stuff. But at some point, it's either going to get too expensive or we're just not going to be able to get it anymore. And it's not in the immediate future because, like I said, we've increased what we call our reserves, the amount down in the ground that we just haven't got out yet, but we think we can. Um, we have enough of those reserves of oil and coal. It's not like we store it up somewhere. It's still in the ground. We just haven't got it out yet, but we know how much is there. And so we've still got quite a bit of coal and natural gas and oil. And we're getting to where we can get more natural gas than we have in the past, partly because it's so expensive now that it's worth, we could do it back even in the 70s, but it was just too expensive. It wasn't worth it. But now the price of gas is high enough, or natural gas is high enough that it makes it worthwhile to do it. Okay, so anyhow, it's not happening anytime soon. I'll be dead. Who knows? Maybe you'll be dead, and it'll be your kids' problems or my kids' problems to worry about. But at any rate, at some point we're probably going to have to do something, and I don't see that right now. Solar and uh, wind and so forth, they help, but they're not going to be strong enough that we can use them all the time, 24 hours a day, 365 days a year. They help, but they're not going to replace other types of energy. So at some point, I think nuclear is a possibility. But something to think about, every energy source is nuclear. What? Someone says, I don't like nuclear energy. Well, technically, it's all nuclear energy. Okay. And someone says, well, I don't think that's true. Okay. Well, first of all, think of this. Most of it is all solar of one sort or another. Okay. Gasoline or crude oil. Where does that come from? Well, dead plants and animals, sea plants and animals that got trapped underground. Okay. Where'd they get their energy from? The sun, okay? And then they trap that energy and kept just like a tree traps energy, and then we burn it and we get the heat from that was trapped. That's really just trapped sunlight. Well, same thing with these animals. They lived in the ocean. They trapped the sun's energy, and now we're getting that energy out where it's been stored, chemical potential energy, as oil, gas, petroleum, all the different things that come from crude oil. Okay, coal, same thing. So now we're talking about plants, plants that live on land in boggy places and got buried, and then they got energy from the sun, and now that energy is trapped in those plant materials that have been pressed over time until we have coal. Okay, once again, what is that? That's just solar energy. It's been trapped for many, many, many thousands and hundreds of thousands of years, but it's that. Okay, and so it's really solar energy. All right, so it says, well, what hydroelectric? This is where we have dams, and we run water through, let water from the lake through, okay, using I might mention potential energy because we have a dam that piles up the water over here, okay, so you have a high level of water behind the dam. You allow the pressure of all that water pressure to push it through and turns a turbine and makes electricity, okay, but it depends on rain, and rain that's what fills up the reservoirs, right, and the lakes and stuff. Well, that's by the water cycle, and the water cycle is kind of driven by, that's right, the sun, the solar energy that evaporates the water, brings it up in clouds, and it falls back down, then evaporates it back up. It's really all run off solar power. So that's solar power. So what else? Wind. Well, wind is when the air heats up over here and rises, and more air rushes in over here. Well, what heats up the air to make it do that? The sun. Okay, so most of these sources can be traced back to the sun, solar energy. And guess what the sun runs on? Fusion, nuclear fusion. It takes hydrogen atoms, squeezes them together, and releases that energy in the nucleus of the atom. And it's a big nuclear power reactor. It's a fusion reactor, which we can't do ourselves yet. We're working at it, but we haven't figured out how to do that yet. But it's a big fusion nuclear power plant, basically, going on. All right. And so it's really all nuclear power. Now, there are a few things we didn't mention. Okay. Well, nuclear power. Well, obviously, that's nuclear. Okay. What about geothermal, the heat inside the Earth? Well, basically, inside the Earth, most planets we think are just solid on the inside, or else made out of compressed gases. Okay. And so any planets that are like the Earth that are solid, and the Moon, for example, are just solid. There is no liquid core, and we'll talk about that next semester if we do. But we have a liquid core. Why do we have a liquid core? Because there's radioactive elements that are breaking down and giving off heat, and that's keeping the inside of the Earth liquid, which is kind of unique among the planets that we know of, okay? But once again, that's a nuclear reaction going on very slowly, just keeping it molten on the inside of the Earth. So that geothermal heat is nuclear fission, which is kind of as things decay and break down, radioactive decay, or fission that's heating up the inside of the Earth. So really, all the energy on Earth is technically, you got it, nuclear. All right. So the question is, how are we going to harness that nuclear energy? All right. Now, kind of got off a little bit there. But you need to know all that. All right. Now, energy does not stay the same. Okay. We said one of the things that is it really can make change, and the energy can change. For a long time, people thought energy just disappeared. Okay, if I heat a piece of paper like that, well, I don't see the energy anymore. It's gone, right? Paper's gone, but the energy is not. This whole room is slightly hotter as that heat from there, that heat energy from the fire, from the paper, was released. That energy that was trapped in the paper was released, but now it's still here. Technically, it's a little bit warmer in this room, and it also used to form some new chemicals, which give us that nice burnt marshmallow smell in the classroom right now. Okay, and so energy must be conserved. There's a law called the conservation of energy, which means energy cannot be created or destroyed. Okay, now there is an exception in nuclear reactions. Okay, in nuclear reactions, we actually have some mass that is destroyed and changed into energy directly. It's kind of weird, and it took Einstein and some other people to figure this out, okay? But barring nuclear reactions, okay, energy cannot be created or destroyed, but it can be changed, okay? It can be transferred from one object to another, or converted. I mean, it can transfer from one object, or it can be transformed or converted from one kind of energy to another kind of energy. For example, when we burned the piece of paper, we converted the CPE, chemical potential energy, into heat. Okay, all right, and so also light. Okay, so several different kinds of energy that came from that. All right, now, but the energy was not lost. It was just converted or transformed. Sometimes you see transform. Transform means to change into something new. So it changed from chemical potential energy into thermal energy and light energy that was given off. Okay, but it can also be transferred. Okay, say for example, if I hit somebody, okay, there's kinetic energy in my fist. Some of it, when it hits, probably gets converted to heat. Okay, all right, sound. You're gonna hear the sound of that, but most of it is just transferred, and then my face spins over this direction. Why? Because the kinetic energy from here was transferred to a different object. Kind of like we have Newton's cradle. We have the energy in the ball dropping down, but then it transfers the energy until the one on the other end pops off the other side. Okay, so it can either be transferred, which is the same kind of energy, kinetic energy, from one object to another object, or it can be converted or transformed into something completely different. Okay, so that's really what we're going to talk about mostly for the rest of this. Well, a little bit other stuff too, but yeah, we're getting there. Okay, some different transformations. Okay, or ways energy can be converted. All right, all right. This is a glow stick. Okay, sorry, I got you. Take this home. You can make the necklace after we finish it. But it has a glass tube in here that contains a chemical. All right. And as long as it cannot mix with the chemicals inside the plastic tube, so you got a glass tube on the inside and then that one, then nothing happens. Okay. They stored the energy, chemical stored energy. But if I break this all along the way, now those chemicals can mix and it begins to produce light energy. Okay. And everybody's favorite kind of glow sticks. All right. And so if I make it sure that it bends and breaks all the way up through there, then eventually those chemicals will mix. Technically, I'd broken it one place before, but it wasn't enough to show up much. Okay, and so now we have light energy. So we've changed chemical energy into light energy, all right, from chemical potential, all right? So that's one example. All right, let's do another. Here we go. All right, these are little balls. They have been covered with stuff kind of like cap guns used to come with. I don't know if y'all remember those. There we go. I can smell it when they work. Okay, I don't know if you can see it, but I can smell it. And it smells like cap guns, okay? It burns off. What's happening? Well, as these come together, there's heat given off. Also sound. You should have heard the sound, okay? But it's being converted. So the chemical energy stored on these balls are being changed into heat. Usually some light. I didn't see any sparks though, and sound. Okay, so it's there. Now, someone says, "Well, I can't really see if there's much sound energy really being heat being converted. We hear about heat friction, but I didn't see much there. So let's try this. Okay, I'm gonna hold this in my mouth. Hopefully, I won't hurt myself. See this? All right. I don't have any lab assistants to hold this for me, so I'm gonna do that. Now, I have two giant ball bearings. Okay, all right, and I'm going to bang them together on this piece of paper. All right, now, ooh, take a good whiff of those. Yeah, you can smell that burnt thing, but you also see those holes in there, okay? Those holes in the paper. What happened? Did these squish the paper? No, if you could smell them, you would smell burning paper, okay? Because when they hit, there's friction. Anytime two objects hit, there's friction. Now, normally it's small amounts and we cannot notice it. Okay, it's not enough for us to notice. But in this case, there's enough mass and therefore enough kinetic energy in the objects that they actually change it to heat and burn the paper. Now, if I did this with another steel ball and used one of my big ones, but this time, so there's less total mass, and they rolled off my other thing. All right. It still made some holes. I don't know if you can see them over here, but they're a lot smaller. Why? Because I don't have as much energy. I don't have as much kinetic energy because I have a lot less mass on this one, and therefore it does not do nearly as much damage. All right, and so when it gets converted to heat, it's not as much, and it just burns little holes in the piece of paper. But once again, we're converting like kinetic energy in this case to heat, as well as, of course, sound. All right. Light bulbs would be another example. This is the filament from a light bulb. You can see the little wire vibrating thing here. Okay, normally electricity flows through this. As it goes through the wire resists the flow and it changes the electric energy into heat, and then eventually it gets hot enough it glows, and it glows and gives off light. So you get heat and light. In fact, most light bulbs that were this kind, the incandescent, the old type of light bulbs, were only about half light and about half heat. In fact, it might give off more heat than it did light. Okay, and that's why they were very inefficient. Okay, it took a lot more power, electrical power, to run. What used to be a 60-watt bulb now only takes like a 23-watt bulb with the LEDs, where they cause light to glow, and the LEDs are a little different. But the fluorescent light bulbs called a gas to glow, and things like that. They use a lot less energy because these converted electricity to light, but they also converted a lot of the electricity to heat. And so if you're in a room with hot lamps, then it will get pretty warm. Okay. Another one, and Mr. McMurray's bag of tricks. Here we have a car, and it has a balloon that's attached to the back end here. I'll blow up the balloon. Oh no, it blew a hole in it. That's not very nice. Okay. Okay, so we're gonna try this one anyhow, even with the hole. I have to replace that, but okay. So we've got this balloon, and we let go, and it takes off. Action, reaction. We know that from Newton's third law. Okay, but what energy do we have? Well, when we blow up the balloon, it stretches out, so it is elastic potential energy. Okay, and as it pushes down, it pushes the air out this way, which shoots it that way, which is two types of moving air, and therefore the moving car, because of Newton's third law, is kinetic energy. So we're going from elastic potential to kinetic energy. Same way if I took a rubber band and shot you with it. All right. All right. Let's see what else we have. Again, physics is just a chance to play with toys, right? That's what it's all about. We have these little racers, which if I rough them this direction and then let go of them, they go shooting off. Now, just for the record, it flipped over and kept on going. Kind of cool little toy there. Okay. Same thing with this truck here, monster truck. There it goes. Question is, what's happening? Well, if we look at the inside of one a little closer up, I don't know if I can get this where you can see it here. I don't know if we can hold that where you do it. When you turn these wheels, there's some gears here, and they crank up, and inside this there's a little round thing here in the middle. I don't know if I can show it to you, but inside of it, there's a coil of metal or plastic, and it's being tightly coiled, tightly coiled, tightly coiled. Okay, then when you let go of it, that uncoils and that spins the wheels. Okay, so just to do it again, if I crank it up, turn those little gears, and they keep winding that little spool inside, that's a elastic type of reaction. Okay, then I let go of them, and the elastic potential energy is changed back into kinetic. So you got kinetic into EPE, and then the EPE back into kinetic. Okay, so it's kind of a double reaction there. All right, you may have seen these described as Chinese handcuffs. So you stick your finger in one of them and stick your finger in the other, and then try to pull out. It gets real narrow and you can't pull your fingers out. Okay, all right, that's one thing. But actually, they are a good kinetic energy storage thing. All right, or actually a potential, because it's, if I squeeze them, let me show you there real close. Squeeze them, see how it bunches up? Kind of like a spring. Okay. If I squeeze it together and then let go, I don't know if you saw it come down on the other side over there. Basically, it almost hits the ceiling. Why? Because you're storing elastic potential, and when you let go of it, it's being changed into kinetic energy again. So once again, another switch. Okay. Now we'll talk about electricity later. There's a lot of conversions made into making electricity. And some of those are after we use the electricity. So, for example, this is a fan, has little plastic blades here. All right, it has a battery. All right, now in the battery, there is chemicals, pasty chemicals that are basics or bases or alkaline. That's what we call them, alkaline batteries. Okay, it's probably a double A in here. Okay, those chemicals have what kind of energy? That's right, CPE, chemical supply. All right, potential, chemical potential. Now, if I turn this, that chemical potential is changed into, starts to spin those blades. Doesn't hurt because it's plastic, of course, but there you go. Okay, it spins those blades and turns it into kinetic. Okay, most of our electric motors either create electricity and we change it into heat, like your hair dryers, which I don't really need, but you know, you get the idea. Toasters, different kind of oven type things, they're changing electricity into heat or very often into kinetic motion, in particular something that spins around like this, okay? And so that's electric into kinetic. All right. However, we can also go the opposite direction, and this is what generators do. Okay, motors take electric and change it into motion. We can also take motion and change it into electricity. Okay, electricity, we'll talk more about this later, but electricity and magnetism are like this. Okay, you hear a lot more about electricity, but you don't hear much about magnetism. But magnets are what make electricity possible in the modern world as we exist. Okay, in this flashlight, there's a coil of gold wire. Hopefully you kind of see that there in the middle. Okay, and then there is a silver magnet that slides in the middle there. Well, it turns out that if you run a magnet through a coil of wires, or if you move a coil of wires over a magnet or around a magnet, it will create an electric current. Okay, so if I do this a whole bunch of times and then I turn this on, it will work for electricity. Why? Because all right, because it creates a current and it stores it in a battery. Okay, and so we can use that. Okay, so you can, I don't know how useful that is if you're running through the woods trying to see where you're going, trying to get away from a bear. I don't know if that's, my recommendation really the best way to do it. All right, but we have another one. Okay, we have another one here. You can see, I think here, the circular thing here, I believe, is a bunch of wires. And then there's a magnet in the middle here. And when I spin this, you can't see it, but it spins the magnet around inside of it. Well, same thing. If you spin a wire around magnets, or in this case, magnets around a wire, okay, it is going to create a current. And if I turn the switch on, it will release the electricity, okay? And so this one at least is a little bit better. You go through the woods running like this. It's still, I don't know if that's going to affect how well you run and stuff, but it will keep a electric current. And if you forget batteries, you don't have to worry about the batteries going dead. Okay. Now, this one's a little fancier. This one has a handle, and I think you may be able to see there's some gears here. Okay. Nice part about these gears is the first gear is a big one, and so it's attached to a little one that's about 1/10 as big. So every time the big gear goes around once, the handle goes around once, the other one goes around about 10 times or maybe more. Okay. And then it's attached to another little one, to another big one, to a little one. And so every time this one goes around, the little one goes around 100 times. Okay, and the good news is that if I do that fast enough, I can create electric current. Okay, and they actually make some of these that you can use to charge your phone out in the woods. Now, whether you're going to get enough electricity to do that, how long do you have to crank it to do that? I don't know, but it is possible. Okay, and that's because in a motor, this is actually a motor, a little toy motor. Okay, and in this case, we're spinning the magnets, so it's creating electricity. Okay, normally we have electricity coming into a motor and it causes the motor to spin around. So we're just reversing it. So now we're moving it using kinetic energy to create electricity, and that's what generators are all about. Okay, motors, on the other hand, take electricity and convert it into kinetic or heat. All right, thermal, whichever, and probably both. All right, I'm not going to take this one out of the package and prove it to you, but because you're not going to be able to feel it. But these are hand warmers. Okay, basically they have sand type stuff, but they have some salt and iron and some other chemicals in there. Those are the main ones, maybe some charcoal. But basically what they do is when you open them and then you start crumpling them together, they begin to react with each other and slowly release heat, and they will keep your hands warm for quite a pretty good long time. You can slip them in your shoes or somewhere, try to keep your toes warm. All right, so they do fairly good. Once again, what are we doing? Energy that's stored in the iron and salt and things. When they release and cause the iron to start rusting, it will release heat. okay, and they will last for quite a few hours, several hours at least, depending how cold it is outside and stuff like that. But they will continue to change chemical potential energy into thermal energy, okay? Kind of a slow chemical reaction instead of like an explosion, which is changing chemical potential energy into heat really quickly, or like when we burn the piece of paper. All right? Okay, one last one. I don't know. We will see. But we have a star here, which is like kind of people put up on their room, okay? But if we let it absorb light, it will change that light back to, no, not dark enough. Let's see here if we can find a dark spot in the house. I like the skylights, but they don't do very good for this. I kind of see these glowing in there, but it's hard to tell exactly. Can't get it really dark enough to tell, but okay. So anyhow, but they are luminous, and basically they will absorb light and convert it, the chemicals that are in here, and then they will absorb, and then when there's no light outside, they will re-emit the light back out. So it's going from uh, light to stored in the chemicals in the star, and then they will be re-released, changed back from chemical light, just like the little bracelet, luminescence, and it will give it back off as light energy. So that's another example of a conversion. All right, one last thing. To do work, we have invented what we call machines. Now, there are 6 simple machines. We're not going to go over all of them right now, but levers, pulleys, inclined planes or ramps, wheel and axle, and my brain is dead at the moment. Can't remember the other one off the top of my head. Um, Anyhow, okay, there are 6 machines. Now, some of these can make widely various types of machines that we don't really think of as being machines sometimes. But anyhow, key thing about machines help us to do work, but they do not reduce the amount of work. This is important. You don't do less work with a machine. The total amount of work stays the same. But what does change is the amount of force that you have to put onto it, and that can work in your favor. Okay, remember, work is force times distance, right? Okay, well, let's say I have a hammer here. If I'm using it to pull up a nail, okay, got a nail here and I'm pulling it up. Okay, notice I have to move the handle, say 6 inches. Okay, and let's just say I put 1 Newton of force on it. Okay, well, you notice that down here where the nail is, it may only go up 1 inch, 1/6 as much. So in order to do the same amount of work, that means the force on the nail has to be 6 times as much. So I put work in at the top where I move 1 Newton of force, 6 inches. 1 times 6, 6. It moves the nail a distance of 1, okay, inch, but that means in order for the same amount of work being done, it has to put 6 times as much force, 6 newtons. 6 newtons of force times 1 inch gives you 6 Newton inches, okay? Sorry, couldn't kind of way to make it into meters without making it complicated, but Newton inches, all right? So it would be the same amount of work. But for me, it's easier because rather than putting 6 times as much force, I can't put that much force on the nail by myself. But now I can move this 6 times as far. I don't mind moving it 6 inches with 1 Newton of force because it puts 6 newtons of force on the nail and takes it out, okay? So it's tempting to say that machines make work easier or make it where we have to do less work. No, we still do the same amount of work with the machine as without it. Okay, but all right, the difference is we may have to put less force on it, which means it feels easier to us. Okay, same thing with scissors, which are another kind of lever. Okay, they're fulcrum here in the middle. They rotate around that. I may move the handles 2 or 3 inches, and the blade may only move like an inch or two. But once again, I don't have to use as much force to cut the paper, okay? Or actually, in this case, it may increase the distance. Maybe this takes more force than it would to actually push the blades together, but I only move, let's look at the blades here, about 2 inches, okay? And they actually cut maybe 3 or 4 inches of paper. And so In this case, it's increasing the distance that's cut. So it puts that force over a longer, less force over a longer distance. I put more force, but it's not that much force to cut a piece of paper, right? So I can handle that, but it magnifies the distance. So machines can either, like the hammer, we say multiplier force, where we have to pull a bigger distance, but we get a lot more force out of the machine, the work that it does on it. Okay, so the same amount of total work, I just have to move more distance with less force to get more force on a short distance in the end of the thing. Scissors can be the other way around. Okay, it's a shorter distance, but I have to put more force. But over here, it puts less force, but over a longer distance, and so it cuts more of it. A broom is the same kind of thing. Okay, if I move a broom right here, I'm only moving 5 or 6 inches, but the broom on the floor is covering a bigger distance. Okay, so I have to put more force to move it up here. It's harder to move it up here than it would be if I actually pushed the broom back and forth on the ground. But I can do more force a short distance, and it will cover a bigger distance and put less force on the ground. But how much force do you need to sweep up dirt? Not much. And if I'm sweeping, I want to get done with it. So the more distance it covers, then that's great for me. Okay, so machines cannot change the amount of force or work that's done. They can change. You put in a little bit of force, and the machine puts out a lot more force over a shorter distance, or it can do the opposite. You put in more force over a short distance, and it puts less force over a longer distance. So we say it multiplies your distance, and you get done quicker. All right, let me check and make sure there's nothing else. All right, there is one last thing, and that is talking about efficiency. Okay, a machine, if I put work into it, and we talk about the work out, we said it has to be the same. Technically, it's going to be a little bit less that comes out than what I put into it. Why? Because our good friend friction. There's friction between the handles here, the blades when they cross. So that friction is going to sacrifice some of my work that I put in. So actually, not only do we say we can only get the same amount, actually we get less work out of the machine than we put into it. Okay, but it still helps us by multiplying our force or our distance enough that it makes it worth our while. Okay, but the efficiency is a little bit lower. And the formula for that is the work done divided by the work you get out, work output we call it, divided by the work you put into it. Okay. And since you always get a little bit less out, that means it's going to always be a little bit less. And so the number on top is a little lower. So you tend to get something less than 100%. An ideal machine is one where you get exactly out what you put into it, and that would be 100%. But unfortunately, that doesn't exist, okay, because there is always friction. And so there are no ideal machines, but we get, maybe if we could get, for example, in this one, maybe I get 95% of my work that I put into it out of it, and that's pretty doggone good. In fact, some things like car motors and stuff, gasoline motors, may only be as low as 50 or 60%. They produce a lot of heat and sound and other energy, where a lot of their work you put into it, or the motor puts into it, does not result in the wheels going around and making you go faster. It's just wasted. Okay, and part of trying to make more fuel efficient cars is trying to get where they're more efficient and they don't waste as much of the energy from the fuel that you're burning. Okay, anyhow, so that is it. I hope everybody enjoyed this. Don't forget, you still got your questions due and your quiz coming up for chapter 6. Have a great week.